Giovanni. Acompanha na câmera aí. Diz. Vê aí no microfone da câmera.
Okay, thank you.
Vê se vai pegar alinhado. Alinhado? Tá, vê do...
Jamais saberá. Я за сколько рассказываю первый примешивание, что я как раз включаю сейчас. Вот, а потом про Ай и про Ай и про то есть так,
Mas o que isso é qual é a nossa próxima aniversário? É o seu aniversário. Quanto que é? Mas, porra, a cara tem 9 de um ano com 53.
É tudo certo. Se tiver nada de esperado.
I'm just I would like 30 seconds ago.
Ok, então.
Bom,
porque ele foi esquecido, eu não podia pensar vocês que botei a culpa nele das coisas, das pessoas acreditadas.
não, tinha que pensar você pegar e
Ainda se pode.
deixar baixado aqui, porque isso é muito. Aí eu baixei assim e tal. Aí eu
So, good morning everybody. Let's start today's lecture. And as usual, we'll start with problems analysis of yesterday's contest. But first of all, I'd like to apologize for what happened yesterday during the contest. The system went down for 2 hours. Actually, the owner of Open Trains assures that this was a one-time thing and it won't happen again. But I believe we have like some kind of backup system, backup contest system now. So probably it won't be as bad as it was yesterday. But I hope we won't have any troubles during the rest of our training camp. So, and now let's begin our analysis. We'll start with the problem A. So, the problem statement was you had a string with different Latin characters and you needed to connect several pairs of equal characters so that connected pairs did not intersect. They could be one inside another, but they couldn't intersect. This problem is standard problem on dynamic programming on subsegments. You need to calculate some function, we'll call it dp, as usual in dynamic programming. And this function is maximum amount of connections possible on some subsegment of our string. Subsegment is given by two indices L and R. And so we have three options every time we need to calculate. We have three options every time we need to calculate value of this function for some subsegment. First option, first option if we don't have like top left wire or top right wire connected to some top left wire actually connected to some other wire, then we can just use a value of dynamic programming function for the subsegment who is inside our subsegment but is shorter on like 1, so it's 0.1 in the presentation. So if the top left wire is connected to some other wire, then we need to find the wire to which it is connected. So we can just check all wires inside our segment. And a formula is on the screen, formula to calculating value of dp for LR. We just connect the top left wire to some other wire, this one in formula. Then we use the segment inside of our new connected pair. It's dp L plus 1 M minus 1, and then we use our calculated value for. Then we use calculated value for the rest of our segment. Then we choose the best option and we store this choice to recreate the answer, to restore the wires. I guess many of you are familiar with the concept of subsegment dynamic programming. I'll just remind you that often when we are solving problems like this, we need to like calculate answers for all segments in order of increasing its length. So you probably don't want to write like for L. You probably don't want to like iterate over both borders. You want to iterate over like lengths and so this won't be correct like order of calculating all segments if we consider L and R as borders of our segment. We need to iterate over lengths of our segment. And then we need to iterate over left border of our segment, and then it will be it. We can call it, I don't know how, plus. And then we are gonna calculate answer for segment I plus L. In this case, we iterate over all segments in order of their lengths, and we have all segments of shorter lengths already calculated, and we can use it for calculating our current value. So that's it for problem A. If you have some questions at this point, you can ask them right now. I remember that I asked to ask all questions you have exactly in the moment you have it. Let's proceed to problem B. So in problem B was one of the two problems about LCA in this contest. And actually one more thing about problem A was that actually we had n in third degree asymptotic runtime for our solution but the constant were pretty small. The constant was pretty small, so it would possibly pass the time limit. But it also is possible that you have to do some non-asymptotic optimizations to fit in time limit. So I don't know how to say it in English, but like you'll probably need to push your solution hard before it passes.
Isn't it 1 plus dp L plus 1 m minus 1 plus dp m plus 1 r minus 1?
I guess it's actually m here and r here. Yeah, this is probably cheaper.
Because it shows m, so you can't choose it again.
Oh,
When you can choose r.
but you can choose r. So the correct formula is 1 plus dp L plus 1 m minus 1 plus dp is plus dp m plus 1 r. Yeah, okay. I'll try to fix it before sending the presentation to our website. Okay. Yeah.
Sorry. Isn't there any asymptotic optimization, like any trick to do in this case, or is it really cubed?
I guess. Well, I don't know about any like asymptotic better optimizations, and after solution for model solution for this problem was also with this asymptotic time, so probably no. But actually, there will be a problem later for which model solution wasn't the best solution. So I don't know. But I don't know about any better solutions than this. And actually, I believe that time limit for this problem was not standard also. It was
6 seconds.
Yeah, it was 6 seconds instead of 2. So like 6 seconds and around 1,500. And in third degree asymptotics, it's probably it. Okay, so proceeding to the next problem. In the next problem, you were having a routed tree with some vertices and a lot of queries of them that look like this. You were given a tree. Every query was a set of some vertices of this query, and you needed to find amount of all of vertices which are ancestors to at least one vertex in this set. So in our case, the answer will be the answer will be like these vertices, and these vertices. So it was first problem for 2 LCA problems in this contest. The next one will be the next one. And so what we can do to answer our queries is I'm sorry. Okay. So yeah, okay. So we need to order all vertices from all the queries in order. Like for every query, we need to order all vertices according to the time they were first visited by DFS. We actually discussed writing the DFS with time of entering the vertex yesterday. So here we can assign its entering time to every vertex, and we can order every query in time. We can order every query in time according to this time. And actually we need the depth of every vertex too. But, oh yeah. So, what we need to do to answer every query. Oh, I left the thing that removes from board. For every query, we need to check all the vertices in our order and calculate the last common ancestor, longest common ancestor. Calculate the LCA for every consequent pair of vertices. And so, when we are calculating the LCA for some pair of vertices, we know that there is an LCA. He has a depth, I don't know, like V LCA. This vertex have a depth V eta, so it doesn't matter, and this vertex have depth V eta. So we know that all these vertices on the route from VLCA to from VLCA to V eta to Vi was already like in our answer, and we know that all the vertices from route to LCA were already in the answer too. So when we are adding, this is I plus 1 actually. When we are adding vertex number I plus 1 to our query, we just need to add like only these vertices to our answer because they weren't in it before. And after that, an answer will be correct answer for first I plus 1 vertex in our query. So since we have our depth, we can just calculate difference of depth between vertex number I plus 1 and vertex and their LCA, and just add this amount of vertices to an answer. Actually, here I believe we can use almost any LCA algorithm you know, and which works in logarithmic time. That will be okay, and total runtime will be m times log n. So, any questions? Okay. Then we are proceeding to the next problem. And the next problem was the second problem in this contest about LCA. And actually, this problem was discussed in details yesterday, I believe. But we'll still discuss it again tomorrow. So, what we need to do two operations with the tree. We need to change a parent of some vertex, and we need to find an LCA of some pair of vertices. I guess that's exactly the problem we discussed yesterday. So we need to construct the Euler tour. It's just the order of DFS visiting three vertices. For some simple tree, it will be like that. 1, 2, 3, 4, 5. 1, 2, 1. 3, 4, 3, 5. 3, 1. And we need to store a depth of every vertex near this vertex a number. After that, we have if we store this Euler tour of this graph in some actually in Cartesian tree, in implied Cartesian tree, we can do the operations of changing the parent. It's pretty easy. We can just like take the segment for some vertex. It will contain the Euler tour of all its subtree. Then we can cut out this segment and move it to some other place. And when we so to move it, we need to find the vertex which will be its new parent. Let's assume it will be 2. We need to add another copy of 2, and we need to insert this segment between these two copies. And after that, to find LCA, we actually need any occurrences of the numbers of the vertices we need to calculate LCA for. And we need to find the vertex in between these occurrences with minimal depth, and that will be an LCA. So I guess that's it. Some thoughts about runtime are on the screen. I guess. Oh yeah, and actually the thing I said yesterday but forgot to say about it today. When we are moving some subtree to another place, we actually need to change all its depth. It can be done with a method kind of similar to segment tree with range operations, with range update operations. So if we have, I'll tell about it a little more. So if we have some Cartesian tree, and we need to update keys in all, not keys, values. We need to update values in all vertices. We can just store some kind of additional information in every vertex, and this additional information can be called update, and it stores like total amount we need to add to every value in our subtree, and then we can during some interaction with this vertex, we can actually set update to 0 and like push it to the children of this vertex, so that our vertex had correct values and had update equals to 0. Someone tried to ask something? No. Okay. So yeah, we just need appropriate data structure, and this problem will be solved. Yeah.
my main problem, like trying to think how to code it, was when I want to move a vertex, I must have like the first occurrence on the earlier two and the last one. And how do you keep that? Like you're dynamically changing like the array and moving stuff around?
No. You see, when you are writing the Cartesian tree like this, I guess you don't want to use an arrays for storing it. I guess you want to use objects for storing it. And then you can just have links from, for every vertex number, you can just have links to two objects which are the first and the last occurrence. I guess that will work here.
No, but I know like the link, but I have to keep updating them.
No, you don't have to keep updating them because the object stays the same. You don't change. Oh.
But even if you keep it, how will you split the tree exactly at that point? Knowing only the vertex, because when you're going down, you don't.
Okay, well, if you have a link to a vertex, you can go up to the root and calculate the amount of vertices to the left from this vertex, and then split by this amount. So, yeah, maybe I should draw some pictures about it. So, if you have a tree, every node here is like an object, and for every vertex number, you store links to top left and top right vertex, top left and top right occurrence of this vertex number. So, like, you know that vertex number 1 first occurred here, and last occurred, for example, here. No, that's not possible. No, that's possible. So, when you need to cut out some part of this tree, you need to, I need a chalk of different color. When you need to cut out some part of this tree, you need to do it by like these two vertices. No, like this. So, since you have an implied Cartesian tree, you need to find amount of vertices to the left of the top left, and you can do it by you actually can do it by storing in every vertex the size of its subtree. You'll still need that for all other operations with Cartesian tree, and then you can walk up the tree to the root and find the amount of vertices to the left. It's actually not so hard to do. It works like if you come to some vertex from the left child, you just have to, you actually don't have to add anything to the amount of vertices to the left of this vertex. And if you came from the right child, you need to add the size of the whole left subtree and this vertex to amount of vertices to the left of the vertex we are looking for. So after that, you split by this amount, and you have like the segment that you need. So, any other questions? Yeah.
To do that, you need to also store for each node the parent pointer to the parent. You need to go up.
Yeah, you do. But really, yeah, it's not too hard to store the parent also. So, yeah, actually, implementation of this data structure takes some time and effort, but but it can be done in like some reasonable time. So, and I think it's a good training for writing, like complex code, but like ACM code. So you need to write some very long program, very complicated program, but you need to do it in like very short time. So it's good training. Okay, so we're proceeding to the next problem, and the statement of this problem was actually quite easy. We need to find some queries. We need to answer some queries, and the queries looks like find kth non-palindrome substring starting from position E. So I don't know what else to say about statement of this problem. So let's proceed to the solution. What we need to do here, we need to find lengths of every palindrome with center in. For every symbol of our string, we need to find the length of palindrome with the symbol in the center. There is a standard algorithm for it. It's called algorithm Mannekers algorithm, and it's modification of that function. Do I need to tell about it? Yeah, okay, I need to tell about it. So let's remember how that function works first. We'll need it actually in one of the next problems. So to calculate that function in some symbol, we store some range. Like, okay, let's start from the beginning. What is that function? That function is length of the substring starting in each symbol equal to the prefix of the string. So how are we calculating it? Well, first of all, we can calculate it in like n squared time by just iterating over string, iterating over substrings, and then just checking if they are equal. But let's try to optimize it a little bit. When we are calculating that function value for some index, let's consider all the other segments before that were equal to some prefix. So it will be like 1, maybe 2, maybe 3. No, it will look like that. We know that all the green substrings are equal to some prefix of this string. So what do we know now? Now we know that let's consider the substring with the top with the largest right border of all these like green substrings. We'll consider the one with the largest right border. So we know that this segment is equal to some segment here because of because this segment was equal to some prefix. This segment is equal to some segment over here, and so to assign some value to that function in this symbol, we can just look at the value of that function in this symbol, because these strings are equal. But actually, if that function here is larger than length of this blue substring, then we just have to cut it by the blue substring. So it's like if here it was some long substring that was equal to a prefix, then we don't know actually anything about this symbol. So we have to assign to that function here some value which will be minimum of length of this substring from our symbol to the top right border of some segment, and that function in corresponding symbol here. And after that, when we assign some initial value to that function, we can just like go and check.
Больше пиши.
Чего больше? Боже мой. And then when we assign some initial value to that function in our position, we can just iterate over all the symbols after our initial value and check whether they correspond and increase the value of that function. And this algorithm is actually work in linear time because every time we check some pair of symbols, we increase the largest right border, so it can be increased like only n times, and so total runtime is linear. Well, this was the that function. This is like pretty common algorithm, and there is a modification of that function which is called Manneke algorithm, and it calculates lengths of palindromes. So how it works? We need to calculate size of palindrome over some position in our string. Well, let's consider the longest palindrome, the palindrome we had before with the largest right border again. So we had some symbol here, which had a palindrome like this. It's not equal, but that's okay. No, I'll enlarge my string. We had some symbol here which had a polynomial with this length, and this length like overlays our current symbol for which we need to calculate our function. We may call it Manneke's function, I don't know. So what we know? We know that this string here is equals to this string here. No, reversed, but that actually doesn't matter in this problem. So we know that if we need some initial value for our palindrome length for our symbol number e, number I, then we can check the symbol here, what value of this function it had, and it probably can be used as initial value for our position number I. Again, we need to check if the length of palindrome here doesn't go out of our longest segment. So we just need to check it every time we assign the initial value. And again, after we assign the initial value, we can check several next symbols if they match and increase our polynomial length. And again, it will be done only linear amount of times. And so this algorithm works in a linear time and calculates all the palindromes. So, anybody have any questions? Anybody? Okay. So, now we know how to calculate all the palindromes. Let's solve the problem actually. Well, the second point of the slide is some trick you can use to eliminate the difference between even and odd lengths of palindromes. You can actually insert a lot of trash symbols between every consecutive. You can insert one trash symbol between every consecutive symbols, and you won't have to worry about even palindromes anymore. So after that, we have some queries. Let's see how our information looks now. We have some ranges. We know they are palindromes, and we have centers of these ranges. We have centers of these ranges. So, we need to find a kth palindrome. So let's look at some position for which we need to find an answer on the query. Let's say this position will be here. Okay, it will be here. So, what strings starting from this position are palindromes, and how can we figure it out from our information about palindrome lengths in every position? It's a question to an audience.
For every center you have after, it is for sure palindrome.
For every center you have after, well, that's not completely true. There is a center after, but it doesn't add another palindrome to this position.
The difference between the result of the manager will be greater or equal than the shade minus the position.
I guess you want to say right answer, but you could have said it in like simpler terms. You could have just said that for every, like, I don't know, we'll call it for every this palindrome, its left border should be to the left of our position, and its center should be to the right of our position. So yeah, that's it. And that will mean that we have a palindrome starting here, and we can even calculate its length, though we don't actually need to do it in this problem. So after that, we know that all the strings starting at this position. Well, I wanted to ask if we need to find lexicographically, but it's equal to the length. So we know that lexicographical order is equal to the length here, because it's a string starting from the same position. So actually, what we need to do, we need for some position find some length which contains exactly k-1 palindrome centers and palindrome centers with their left borders to the left of our position. So if we need to find actually no. Yeah, the last part I said wasn't true. So we need to find we need to find the range that the amount of cells in it which are not palindrome centers, or their left borders aren't to the left of our position, is exactly k-1. Yeah. So I guess I'll just draw another picture and it will be better. So we have our string, we have a position for which we need to calculate an answer. An answer is string this length, and in the string there are two kinds of positions. One kind of position is palindrome center, which contains left border to the left of our position. We'll call this position like bad position, and another kind is good position. It's either a palindrome center which doesn't contain left border to the left of our position we calculated before, or it's not even a palindrome center. It doesn't have any palindrome starting in it. So we need to find the length in which there are exactly k-1 bad like positions, and that will be our answer. So how we solve the problem for all the queries like one by one. Let's sort our orders in let's sort our queries in decreasing order, and then go iterating over our string from the right end to the left one. We'll store like 1 for every palindrome center we meet, and we remove this one as soon as we pass the left border of this palindrome center. After that, we need to find, actually it would be better to store all ones and zeros for these palindromes. After that, we need to find just to answer the query, we need to find just a segment with its total sum of digits here equal to k minus 1. So that can be done with either some segment tree or binary search and Fenwick tree in log square time. So actually this is standard algorithm. I guess I don't have to tell it. But actually, if someone has any questions. Yeah?
You were saying that the center of the palindrome is a bad position. The center of the palindrome that reaches your position 9. Isn't it supposed to be the opposite side of the palindrome?
What? Can you maybe come to the board and ask, because I don't get your question. So.
You have here your string.
Yeah.
Here's your position 9.
Yeah.
Here's your palindrome center.
Okay.
And here it reaches there. Okay.
Yeah. Okay.
So you're saying that this is the bad position. It's supposed to be here, like the mirror of this distance, because here the palindrome ends starting at I.
Yeah. You know, me saying this is a bad position doesn't actually mean it's bad. We just need to like differ two kinds of position. This one's which has like palindromes starting at I and going through the center and going here, and other ones that doesn't have this palindrome. Since we are finding the kth one that doesn't, that is not a palindrome, we just call it bad, but we can like change this. So yeah, this center does give us some palindrome, and that's actually the center does give us a palindrome.
Thank you.
Okay, I guess that's it for problem D, and we can proceed to problem E, and I can say that it was the hardest problem of the contest. So prepare yourself. Actually, even statement is the longest slide with a statement, and statement in like printed statements was also the longest. So what we need to do? We need to calculate total amount of the bribes given by some person, and bribes are given by some rules. Like if you have passed some guards with a rank less than rank of current guard, you need to find the median value of the bribes you gave to these guards and add 1 to it and pay the bribe to your current guard. So actually the statement is on the slide. I hope you everyone read it yesterday, so I'll proceed to solution. First of all, let's do some like general observations about how we will solve this problem. First observation is that actually every person pays the same amount of money on some edge, because persons doesn't interfere with each other payments. So if some person came to some edge in our tree and walked some way from the root to this edge, to this vertex, it paid some set of bribes, and this set of bribes is the same for all the persons. So we can just find the amount of the size of bribe he pays on this edge, and after that we'll easily find all the answers, because we can calculate a total sum of bribes on the route on the way from root to every vertex, and that will be all the answers. Yeah, and another observation is that the size of bribe paid here depends only on the size of bribes and ranks of guards on this way. So what we can do to solve our problem, it probably is written on the next slide. Yeah, we do our DFS search in our tree starting from the root, and we maintain some data about the bribes we were paying before. Which data we maintain, I'll tell later. For now, it's just like general idea of how are we solving this problem. And then we find the size of bribe for every edge, and then we calculate total size of bribes for every vertex, and then we solve the problem. So let's look at what information do we have when we came to some vertex. Actually, it's written on the screen, but I'll spell it. We have some amount of pairs which describes bribes. So every pair contains from rank of guard we paid this bribe to, and amount of money we paid to him. Actually, we have greediness, but greediness, we don't need greediness anymore, because we don't need it. So this data can be represented as a set of points on the plane with two axes. One is size of bribe and the other is rank. So what should we do with this set of points to find the size of the next bribe? First of all, we need to consider only the points that are lower than some border, and this border is a rank of our current guard. We need to find the bribe size too. And second of all, we need to find an appropriate vertical border to separate the half of all points from the other half of all points. Actually, let me see. Okay. Actually, one might say that this border can be binary searchable, and actually, model solution for this problem was based on binary search, and it worked in log in third degree n time. But I guess we have a solution that works in log in squared time, and it's not harder than solution with binary search, so we'll do it a little bit differently. Let's consider a segment tree, and every leaf in which will correspond to some size of bribe we can pay. As it's written, there can be a lot of leaves in this segment tree, but that will be discussed later. And so, for every vertex of the segment tree, we need to store a set of all points in its subtree. So, we have, I'll draw a picture to illustrate it a little bit. So, we have several vertices. First corresponds to bribe size 1, second corresponds to bribe size 2, third to bribe size 3, and fourth to bribe size 4. Oh, 4. Yeah. When we need to add a new guard we pay the bribe to the structure, we need to add it to corresponding leaf with corresponding bribe size. Then we need to add it to the set in this vertex. Then we need to add it to the set in this vertex, and so on. So we need to add it to all the sets on the way from root of segment tree to the vertex with corresponding bribe size. And points inside every vertex are stored in, well, it's written Cartesian tree, but actually it's as written any other binary search tree. So we need to store all points in every vertex in some kind of binary search tree ordered by rank. So we need to do some interesting queries pretty quickly. So what we do to calculate the proper size of bribe to calculate the proper size of bribe to bribe some current guard. As in one of the previous problems, we traverse down the segment tree, and in every vertex, when we are deciding to go to the left or to go to the right, we can find amount of guards with rank less than ours. And based on this amount of guards, we'll decide when we are going to the left or to the right, and finally we'll come to the leaf which corresponds to the bribe size we need. So the the constraint on the traversing the segment tree is Okay, so we are standing in the root and we need to decide whether we are going to the left or to the right. How do we decide it? We take the left child, we throw a query to him which calculates the amount of guards with less ranks, with ranks less than ours. If this amount is larger than total amount of guards with rank less than ours, not larger, larger than a half of total amount of guards with rank less than ours, then we need to go to the left and find there some point which separates half of the guards from other half of the guards. Otherwise, we need to remember that we passed several guards here, go to the right, and then find the point which separates half of guards from the half of guards. So total complexity is written on the screen. It's important that it have one log n and one log max c, because we have a segment tree with a lot of vertices and height of logarithm of maximum size of bribe. So what we need to do to have that segment tree? It's obvious that it can be stored in memory, like in array, like we are used to. So we need to make it, well, I don't know again how is it properly called in English, but we can do it like lazy way. We can create our leaf and all the vertices on the way from root to this leaf only when we need this leaf, and if we need it, because we don't actually need all the leaves in our segment tree, because there won't be so much bribes to fill them all. So we need to create only the leaf when we need it. We need to create all the way from the root to it, and that will be it. So if we are talking about implementation, then this segment tree won't be stored in like array with nice indexes, but it will be stored in objects and it will work just fine. Because if we have like all the queries going from the top of the tree, that's okay not to have all the vertices. So, any questions? Yeah.
Can't you just compress
The bribes?
It may be the option if we knew right away all the set of bribes we will pay. But we don't, because we pay like greater bribes than we gave to a previous guard. So no, you can't. But that would be the option if statement was a little bit different. So, any other questions about problem E? I'll leave it at the last slide of problem E. So, let's proceed to the next problem. Next problem is called scarf, and it was actually, I guess it was the easiest problem of the contest, but I'm not sure. Maybe it's not true. So, what we had in this problem, it was scarf consisting of a lot of segments, and we were folding it by some rules. Rules looked like this. If we had some iteration, we had scarf like this, then I'll draw it with different colors again. Oh. Then after the folding, we had something like this, this, and this. And this was exactly the half of the size of the scarf on previous iteration, and the height was increased exactly to exactly multiplied on 2, and etc., etc. So what we need to do here, we just need to simulate our process to find an answer, because we have only like, I don't know, 50 maybe or 60 something iterations in our process. So we need to store all the like parameters of our scarf. There will be only 4 of them is enough to like have all the information about the scarf. length and height describes the scarf itself. What height does it have now and what length does it have now? And seg position and seg height describes our segment we are looking for in the final scarf. In which position from the left it's now and in which height. So length and height are changing in a simple way. Every iteration we just multiply one on 2 and divide the other one on 2. And after that we have, for 2 other variables, we have 3 different cases. And on the next slide is, I guess, analysis of all the 3 cases. And I hope it's true. So any of these cases we can easily find how to what happens in this case. So the easiest case actually is the second one, when our segment lies between 1/4 and 3/4 of the length of the scarf, then its position only decreases by 1/4 of the length of the scarf, and its height doesn't change because we don't fold this part of scarf. And the other 2 cases, actually you can check the formulas, I guess. If I need to explain, please ask. But I think that you can understand them. So height is changed similarly in both of these cases, and position is changed. How will the position change? Okay. So, it's a slide we don't need. If you have any questions about scarf problem, I'll be glad to try to answer to them. Otherwise, we are proceeding to the problem G. So, what did we have in the problem G? We had some square with reflectable walls, and we had some light ray which goes from the bottom left corner to the top right corner, and it can be reflected from the walls, and it shouldn't hit 2 other corners, and it should get to the top right corner. Yeah, it goes from the bottom left to the top right, and it should hit top right corner after exactly k reflections. So let's change our problem a little bit. Let's reflect square instead of reflecting ray. In this case, ray goes straight and it goes through some what is it, squares? It goes through some squares, and if it's hitting a corner, he is actually hitting in a corner in the original problem, but not always top right, but we'll discuss it later. If it intersects with some square border, it actually reflects in the original problem, and if it comes to the corner in some conditions, it comes to the top right corner. So which conditions do we have on size of this size of this like square field? I offer you to name these conditions, and then we'll check if it's true. So when do our ray get to the top right corner? What should be n and m here?
N plus m should be k. K plus 2.
Yeah, that's actually true. That's first condition. Yeah, that's first condition. It's not hard to find it because when it goes from the bottom left to top right corner of our square field, it crosses exactly n minus 1 plus m minus 1 borders, so it reflects exactly n minus 1 plus m minus 1 times. So it, yeah, that's first condition. Other conditions.
The GCG should be 1 on m.
Hmm?
N and m should have the greatest common divisor of 1.
Correct.
Yeah, that's true. And Okay, we'll just say okay, so the n m equals to 1. Okay, yes, that's true, so that we won't hit any other corners on our way. And the final one? Both of them? Both of them are odd, but actually in this case, why odd? Oh yeah, okay, I got it. Okay, so actually we need their sum to be actually we need their sum to be odd, because in other case we won't hit the top right corner, we hit some other corner, and that's not what we need. But actually we need it to be plus m mod 2 equals to 0. Yeah, that's actually all the conditions we need. They are written here with explanations why do we need it. And that's the answer for our problem. So, phi here is Euler function. Who knows what is Euler function? Okay, not all of you. And who knows how to find it for any like number? Okay, not all of you. Okay.
With the 4.
With the 4, yeah, that's kind of true. Okay, so I'll explain a little bit about it. We still have some time to go, I think. So, Euler function is the amount of numbers which are less than n, but which are less than m and are co-prime with n. So in this case, we need to find all the numbers which are less than k plus 2 and are co-prime with k plus 2. And it's easy to understand that if the first one is co-prime with k plus 2, then the other one is co-prime with the first one, and then we have one of the answers. So, how are we calculating it? Actually, there is a theorem that proves that Euler function for the multiplication of two different numbers is equal to multiplication of Euler functions. Yeah, if they are co-prime. So, what we need to do here? Okay, we need to find a way to calculate our Euler function. So, how are we doing it? We have this theorem, and then we can find. We can factorize. Yeah, I was looking for a word. We can factorize our number for which we are calculating Euler function, and calculate Euler function simultaneously for all the primes in their degrees, and then multiply all these Euler functions and get an answer. So, how are we calculating Euler function for some prime in some degree x? Some prime number in some degree x actually has exactly px minus px minus x minus 1. Yeah, px minus p and degree x minus 1 co-prime numbers with it, because it's all the numbers which doesn't have p as their divisor, and that's it. So we're calculating these values for all the prime in their degrees for our chi plus 2, and then we multiply it on each other, and then we get an answer to our problem. So, any questions? Okay, then we proceed to the next problem. It's called problem strings, and it is about strings. We need to find all substrings of string A that occur in B exactly k times. So, actually, this problem has a lot of solutions also. It probably can be solved with hashing. It definitely can be solved with some suffix data structures. But I'll tell you a solution based on that function. We already have discussed that function today. It's nice. And for this, to solve this problem with the function, we'll need first to divide it on several different problems. Each one of them will solve. So let's now solve our problem for all the suffixes of the string A, like independently. So the statement of the new problem is written on the screen. Actually, we need to find all like substrings that start in some position I and occur in the string B exactly k times. And actually, if you think about it, we can skip some of these strings because some of these strings can occur in A before. So we may have like this string here and this string here. Then we can skip it and find only the amount of strings from here to here, which occurred in B exactly k times. So we'll discuss how to find these values as eta. They're called as eta, I guess, maybe because of start eta. I will discuss how to find them later, and let's discuss how to solve our problem yet. Let's take some suffix of our string A. We have our string A. We are taking some suffix of it. And concatenating it with some trash symbol and string B. And let's find that function of all the string. So, if we then need to find how much some substring starting here occurs in B, we need to find all values that are all values of that function here that are greater than length of our substring. It's actually written on board, but it's not hard to understand because, like, if we have some z function value that is greater than the length of our substring, then this substring occurs and some other things after that, but that doesn't matter. So we need to just calculate these values for all the substrings which starts in I, and that would be the answer for every I. Another thing, yeah, we can do it in linear time as it's written on slide. Actually, it's not that hard, but I'll explain how. We need to just find amount of occurrences of every value of that function. Yeah. So we need for all positions of string B, we need to do something like that plus, and then for every possible z function value, we can easily calculate total occurrences of z function values greater or equal than it by summarizing some suffix of our CNT array. And after that, we have only one problem. We need to exclude the strings that we already have met. Actually, it's not. I guess it's written on the next slide. How are we doing it? Actually, if we are calculating like z function values for for every suffix of our A concatenated with B, we can just update this start value for every position with that function. So yeah, it's pretty much written. So it's understandable that if we have some string a and we calculate that function for this suffix plus trash symbol plus string b, then and that function in here equals to some value, then we don't need to calculate answer for all these strings anymore. So we can just remember it for every position, and when we come to this position, we have already a correct like start value for right border of the substring starts in this position. I guess that's it for problem H. Yeah, okay, total complexity is O(n squared. And that's okay because we had two strings with lengths no more than 10,000, so it will work. And actually the model solution for this problem works in squared time too. So I guess that's how it was. I guess it's the correct solution. Okay, so that's it for problem H. I guess we'll make a break now. And after that, we'll discuss the last problem and some algorithm you're gonna need to solve it. Yes.
Смотришь, что еще можно рассказать?
Если план составил.
А?
Чем? Я план составил. Я
ответственный молодой человек. Какой план?
Ну, того, что рассказывать.
На все дни или на сейчас?
И сейчас.
Сейчас норм.
Он все еще работает.
What do you do? You just populate the process. So it can start. It's part number. Oh, it's query. So first, let me process. How? First case, your iter is less than 1/4 of the length of this code. What happens in this case?
Sim, eu botei a que estava na tomada aqui na base, que é mais fácil da gente destrocar, se for o caso. As outras baterias.
Da base consome mais.
Cadê a outra bateria?
Tá carregando lá. Eu pego.
No, actually it's not. It's two heights of scarf previous iteration minus its height, and its position like changed in I guess 1/4 of the scarf minus last position. So the second case is so its height didn't change because it wasn't folded over. Its position was just increased by 1/4. And the third one is and its height changed like changed here and its position changed like I guess
Caneca, né? Pra não ficar gravando.
Esse vai desligar o stream.
Ну, такие слайды, что я добавить, что можно делать важно потом опустить, а он говорит, опускать. Единственное, что у меня ноут, кажется, садится. И это может проблема. А, нет, это проблема. Ну, давай.
Deixa eu pegar pra baixo.
Então você queria falar. Caiu na internacional da a última parte da boa, boa. Não sei, vai ser. Eu te dou R$1.000. Só posso? Oi. Eu pagamento. Posso e às vezes aquele
for some time now. Yeah.
Really? So that
Again, of course. Okay. Like, could I sit down? I can make guess 20.
Fala o nome aí. Fala, grita o nome aí, Gustavo. Nome, vai pôr o nome. Você chega no Então, o caminho do mercado, ele recordava e passava. Esse problema lá, ele falou, você vai estar peraí. 6 minutos depois estava passando.
Eu perguntei pra ele se acho que meia hora aí ele parou, pensou, aí ele pensou, tipo, não é provável.
Senhor Mandício.
Okay, I think that's enough audience for me to start. So I wanted to have today's lecture on FFT, the fast Fourier transform, and I'd like to have it as full as possible, but we'll see. So the fast.
I'm sorry to interrupt you. I have to just turn it on so the camera will follow. You will turn it off. Okay.
Great. So, don't misspell this word. Okay, so why we wanted to have the lecture about this? Well, first because the last problem remained in the contest was solved using fast Fourier transform, and because it's kind of becoming a popular theme, and the last word finals actually had the problem on fast Fourier transform, so it's kind of important for everyone to know this right now. So, what's it for? So, assume we have two arrays. Let's have array A. Okay. So, for all the math I'm doing right now, all our arrays will start with 0, A, and -1, and B. So assume these represent polynomials. So we have AX is the usual sum from 0 to n minus 1. So it's ai times x to the power of I, and b is the same. So, how do coefficients of c, x, which is multiplication of this, how do they look like? So, this is easy. This is just sum over all elements, say P and Q, which have sum equal to I. It's AP times BQ. And it's the same as we just iterate from 0 to I. So it's A j b I minus j. So we have these two indices have the sum of I, and we assume that our indices are all non-negative, so it's equal to this. So the main problem that discrete Fourier transform solves in competitive programming is exactly finding this sum. There are a lot of applications of Fourier transform outside of competitive programming, of course, but I'll just talk about the uses for problem solving. Okay. So, and one note, this array C is called a convolution. So, like this is the convolution. Okay. So we need some prerequisites to know when we can apply fast Fourier transform, and I'll speak somewhat abstractly first, but then we'll go into details later. So assume we have some field f. Field is a set with two operations, and neutral elements for each one. So, and assume we have some element omega, which we call the root of unity. Okay. Omega is the root of unity, which means n. So it's n's root of unity, which means that omega to the n's power is 1, and omega to the kth power is not equal to 1 for all k from 1 to n minus 1. So these are all, of course, different and are not equal to 1, and n's power is equal to 1. Okay, so now we define what DFT of an array is. It's just another array of the same length where it's evaluated as polynom. This one, the first element is evaluated in point, which is omega to the power of 0. The next one to the power of 1, and so on, n to the power of n minus 1. So this is what discrete Fourier transform is, and we'll later build an algorithm called fast Fourier transform to compute this in n log n time. Okay, cool. So let's do some kind of obvious properties first. So let's have an index here. So to say that it's the nth root of unity, and we'll later need different roots of unity. So we have n here and n here. Great. And well, everywhere later will require that n is the power of 2. If it's not, well, if it's not, usually for our purposes, you can pad it with zeros to have the length equal to the power of 2. It doesn't always work as we need it, but often it works. So we require n to the power of 2. And one more thing, that nth root of unity to the power of n over 2 should be minus 1. Well, of course, when we square it, we get 1, and here we get to the power of n, which should be 1. And it can be 1 because of this property. So it should be minus 1. Okay. So let's now build the divide and conquer algorithm for this. So let's look at our divide and conquer algorithm for computing the discrete Fourier transform. Okay. So we have this array. First, if the length of it is 1, then discrete Fourier transform is trivial. It's the same array. So if n equals 1, then d of t of a is a. So it's like a constant polynomial. If we evaluate a constant polynomial in any point, we get the same constant. Okay. So now we have n equal to some power of 2. We now somehow divide it in half, compute the DFT of these two halves, and then combine together. Okay. So let's pick any point x. It's sum of these omegas in some power, and we'll see. So ax is sum ay x to the power of I from 0 to n minus 1. So let's split the sum into sum for even I n minus 1 I, and for the odd ones. Are there any questions so far? Yes? No? No. Okay, good. And since we know as n is even, it's the power of 2, then it's even. So let's rewrite these two. So we have here from I to 0 to half n minus 1, a to I, x to I, plus here all the x's in the odd power, so we can have x outside of the sum and have almost the same sum. Right. 2i plus 1, x to I. So here we have almost the same sum, as you see. So these look like DFTs for the small array, and this is also a DFT for a small array. So let's have these two arrays. So the first one will contain even elements of A2, A minus 2. And here we'll have elements A1, A3, and so on. Great. So let's have okay. Right. So let's start our algorithm. So let's call it DFT of A. I'll write in some kind of pseudocode, not in any real language. So DFT of A. Okay. So if length of A is 1, then adjust A. Otherwise, say that M is the length of A. Define those two arrays. So it's A0 and n minus 2. A1 is odd elements, minus 1. Here, let's call the DFT for these two. Let's call it like A waved, I guess. A0, 1, 2, A1. So we know, because of the master's theorem, that if we do some linear work and then call two subtasks of the size divided by 2, then the total runtime will be O, big O of n log n. So now our task is to combine these two guys into a DFT for A. Here we have some useful formulas already. So, good. Okay. So let's have, so these two contain n half of n elements. So let's have the loop for n over 2 minus 1. Is there a question? Okay, sure. So now we have to somehow calculate the elements of DFT of A through these two. So let's see. So let's say so what would AI be? Well, we have the formula for this. Instead of x, there will be an omega to the power of I. So this one is just, we take ith element of DFT for the even, multiply it by omega, we take the corresponding element in odd. So it's just a wave 0 ith element plus omega to the power of omega nth to the power of I multiplied by other element. Yeah. So that's the ith element, and since we only have this element for the first half, we need to somehow derive the elements for the second half. So let's get back to this one. Okay. So let's consider A in point evaluated in point of omega n to the power of I plus half of n. What would it be? Well, it's the same as this one. So we'll just plug this into this. 0 n over 2 minus 1 to I omega to I plus n plus n I plus 1 x to I plus n. So this doesn't really differ from the corresponding term where there is no n over 2. And how can we simplify this? So I'd like to hear from you. How can we simplify this? Any ideas?
I have a question actually.
Oh, yes.
Why there's like an omega on the left side and an x on the right side?
Oh, sorry. Yes. Thank you. Yeah, and it's subscript and everywhere.
Omega n is 1, so omega 2i minus n is omega 2i.
Yes. So do you mind if I just erase this one? Say this one is 2i. This one is 2i2. And what about this one? Yes. So we can erase this n over 2, but this turns into minus. So this will be minus omega I and that's it. It's the same, but with minus here. So here we'll have ai plus n over 2 equals to the same, but with the minus sign here. 0i minus n I. And so that's it. So that's the whole algorithm. It's recursive. It uses recursive calls. And yeah. So like take the time to take a note. And okay. So I'll just use another half of this board. Okay, so we calculated this. What can we do with this? So the interesting part is if we have C, well, let's say the C is a like star B. This is convolution. What can we say about the DFT of C? What does it equal to?
A applied to omega n 0 times B applied to omega n 0 and
Yes. So this is like point-by-point multiplication. So if we have the I here, so it's ith element here, ai. Okay, so now we have compute the convolution in linear time, not in square time like this. And after that, we can apply the inverse DFT to calculate the convolution in n log n time. But we still don't know how the inverse DFT looks. So let's do this. I think I'm done with this board. Great. So the interesting fact that inverse DFT is actually the same. T of a wave is actually equal to DFT of A, just with different omega. So I'll just say it as a subscript, so we use the omega minus 1. So if instead of omega here we'll use the inverse of omega, we'll get the DFT. we'll get the inverse DFT of array, but we'll have to divide it by n, which is the length of an array. So this is pretty easy to check. Well, it's kind of straightforward if you just write this formula. So we want to prove that I DFT of DFT of A is the same as A. Any questions so far? Okay, good. So I'll just sketch a proof here, but I won't write the whole mess. So let's get like what? Okay, let's take an ith element of this whole thing. So AI here is the sum of something minus 1 multiplied by omega n minus I. So here in inverse DFT we use omega inversed. So e to the power of I will be the same as omega to the power of minus I. And it's the same if I wrote n minus I here because it's kind of cyclic. So here will be another sum, n minus 1 of the 1 over n here. N minus 1 of AI omega okay, I messed up. There will be J, there will be K, K, KJ. So this is the ith coefficient of the thing inside, and this is the whole thing. Now from this, we can use the, well, you can prove it yourself. I won't write this whole thing down, but the thing you can use that is that the sum of these guys, K I, is, it's either 0 if K is not 0 and is n if K equals 0. So this is the standard like geometric progression, and if it's 0, it's just sum of n ones, and if it's not 0, then the whole sum is 0. So just you can prove it yourself. It's kind of an interesting math exercise, I'd say. Okay. So to get the convolution of two arrays, so let's write like this. So the convolution of two arrays is the same as if we take the inverse transform of n direct transform of A and just multiply it by transform of B. So this is the main result. We know how to write this function. We know how to write this function just replacing all the omegas by its inverses and just dividing by n afterwards. Great. So far we've been talking abstractly about what is the field. I said the field with the root of unity and nothing said about the real world. So the most common use of this field is just complex numbers. Complex numbers. And here the root of unity would be just e to the power of 2p over n. Right? I. This I is not an index, this is an imaginary one. Okay. So we can just verify that all these rules hold, that to the power, if we raise it to the power of n, what? Yes, this will be indeed 1, and it won't be equal to 1 if we raise it to any other power. So, and the inverse is just the same, but with minus sign. Good. So if we do that in with complex numbers, but often our input polynomials are real. So we just multiply them and take the real part. Okay. So any questions so far? I'm going to move to the examples of problems you can solve with FT. No questions? Okay. Okay, so the first application is multiplying big numbers. So if we have number in base b, let's just for simplicity say that b equals 10, and we'll have some two long numbers, a minus 1, a minus n minus 2, a 1, a 0. And the same is for b. And we want to multiply them in base b, and all the coefficients lie from 0 to b minus 1. So how can we do it? Okay, here we can just pretend that these two are not numbers, but actually polynomials. So say ax is ai, xi, I from 0 to n minus 1. And the actual value of this big number is when we take a of b. That would be the actual number. So the multiplication will be very similar to how we multiply polynomials. Dx. So the Ci will be I B. So, but there is a problem. We can point out the problem here. Hmm? Yes. So some of these numbers can be up to k, and these numbers are not greater than b squared. So this is the upper bound on these coefficients. And it can be, of course, better than b, greater than b, sorry. And we just have to do our standard process of like going from C0 from Cn. Have C0. So we have C0 mod B, and we'll transfer the C0 divided by B. So the like standard school addition. Okay, I just realized I forgot one important detail here. Not in algorithm, but in general idea. So we know that we have our two polynomials A and B, and their degrees are n, and minus 1 actually. What degree would the multiplication be? Huh? Yes. So it's 2n minus 2. And if we do the transform with the size of n, like not all the coefficients of A multiplied by B would actually fit in our array. So the size of DFT, let's say n, should be greater or equal than degree of what we are trying to achieve. So all the DFTs here have the same size, and this size should be greater or equal than A multiplied by B. So for example, if we have one polynomial of degree 6 and one of degree, say, 11, so the sum of these would be, what's it? So degree of their multiplication would be 16, and the size of DFT we should use for this. Actually here, yes, it's even plus 1, because like if we have degree n, we have actually n plus 1 coefficients, so we should have one more than degree. So the n should be the power of 2 and greater than or equal to 17. So here we should use the degree DFT of size at least 32. Is that clear? Any questions? Okay. So, okay. So the numbers are almost polynomials, but we have to like carry out all that's left afterwards. Okay. So another example of a problem I wanted to show you is the Hamming distance for all substrings. So suppose we have two strings. Whatever. And B is like the shorter string. And we'd like to have Hamming distance from this substring to this substring, then to this, then this. So for all substrings of A that have the same length as B, we'd like to have the Hamming distance from B to A. First, let's assume that our strings contain only like zeros and ones, so bit strings. So for example, for the first substring, the Hamming distance will be 3, then 0, then 2, then 1. Yeah. So, any ideas how to solve this yet? Okay, so let's write down what we want. So we have the distance I. It's from 0 to length B minus 1. Is the A I plus J minus B J. This is the Hamming distance with the substring of A starting with position I. Well, since these are bit strings, this is actually equal. We can write this not as absolute difference, but as square difference. Right? So after we expand this, we get sum of squares of corresponding characters in A plus sum of squares of all characters in B minus 2 products J, B, J. So this is the term we are interested in. This can be calculated by just prefix sums. This is constant. So now the problem is to calculate this kind of product. 0 to B minus 1. We have A plus J, B, J. And we have to do this for all i's from like 0 to length of A minus length of B somewhere. So this is the problem which looks like the convolution, but is not quite yet a convolution. So what do you think we should do next with this? Okay. So in convolution, here we have the sum of all indexes with constant sum. But here the sum is not constant, but the difference is constant. So I plus j minus j is constant for all the sum. So what we want to do is transform so that sum is constant instead. So let's define let's reverse the B string. So let's Ci is B length of B minus I minus 1. So if we plug it here, 0 to B minus 1, I plus j multiplied by C, B minus I minus 1. So here we see that the difference, it's j, right? J. So here we see that I plus j plus length of B minus j minus 1 is constant. So it does not depend on j. So here we can see that this is convolution, and we take this convolution at position, let's say, so it's length B plus I minus 1 plus I minus 1. So knowing this, we can now calculate the Hamming distance here, and know all the Hamming distances from B to all substrings of A. Cool. So now there will be a bit delayed tutorial from last contest problem I. Now I'll just shortly remind you what the statement was. So they will have, let's say, the regular polygon, and there were some, and these vertices were colored. So 1, 1, 0, 1, 0, 0, 1. And we wanted to calculate the number of triangles which have two equal sides. Are there any? Yeah, so for example, this triangle has two equal sides. And that all the vertices have the same color. Yeah. So how can we do it? Using the new technique with the polynomial multiplication. So let's just choose one color and say all the positions where this color appears are ones and all the others are zeros. And let's fix one position. Let's calculate all the triangles where this vertex has two equal sides attached to it. How can we do it? Okay, so let's have another picture. And we have this guy here. It's a 1. We just brute force this vertex and calculate. So it has number I. What it means to have two equal sides here? And these two are also 1s. Well, this means that this vertex has number I minus j, and this one has number I plus j. This, we consider this string as cyclic, so if it's less than 0, then we add n to it, and if it's greater than n, we subtract n. So the interesting thing here to notice that sum of these indexes is always 2i. So I minus j plus I plus j is always 2i. And all the triangles that have two equal sides at this vertex also have the sum of indexes equal to 2i. So the number of triangles which have this vertex as its top vertex is equal to sum of 2 n over 2 a I plus j a I minus j. Is this clear? Okay. So basically we iterate over the length of this arc, and we see if this one is 1 and this one is 1, add 1 to the answer. So this is exactly what this formula is doing. So now we see that actually this formula really looks like the convolution of A with itself. So let's introduce our new array B. Which is the convolution of A with itself. So Bi, as usual, is the sum over all pairs of indices, which are equal to I. It's A, P, A, Q. So this is the convolution. And now we will solve this problem using the values of this array. Okay, so let's iterate over all vertices and calculate how many triangles there are where this vertex is the top. So we fix I. We look at B to I. It always contains this vertex because B to I contains AI multiplied by AI. So we don't need this one. And also we calculate the same pair twice, so we divide it by 2. So this is the number of pairs of indices that have their sum equal to 2i and are both 1s. Are there any another triangles that we missed?
2i plus n for the factor.
Yes. So we mentioned here that we have this cyclic, so it's actually equal to 2i mod n. So for example, we can have so for example, if we have one, say 2, 3, 4, 5. We have this triangle, but 3 plus 4 is not equal to 2, but it is equal to 2 modulo 5. So we should also look at B 2i plus n, and also 2i minus n, because of the same problem. If we choose this triangle instead,
Unit index in 0.
huh?
Unit index in 0 for the mod n.
Sorry, don't
4
quite.
plus 3 mod 5 is 2.
Yes,
1.
and yeah, here we have 2i, so we are looking for 2. So here we have 4, and 1 plus 2 equals 3, which is equal to 8 mod 5. So 1 plus 2 is equal to multiplied by 4 mod 5. So we need to look at these three values, 2i minus n. We'll have to look carefully at which values contain something we don't want to add. So for example, if n is even, so we have 2 vertices here, this vertex will be counted as though this is not a triangle. So carefully handle cases where n is even to exclude these guys, and for all I, just look at these three values and add them to answer. However, if there are, for example, if n equals 6, if n equals 6, we counted all the equilateral triangles 3 times. So this is the vertex, since these sides are equal. This is the vertex, since these sides are equal, and this one. So in the end, if the n is divisible by 3, we need to do some additional work to exclude all the equilateral to count all the equilateral triangles. And since we counted them 3 times instead of 1, we need to subtract twice the number of these triangles. Okay, so So that's it for problem I. I suggest that you implement FFT at least once here, and since it was introduced once in World Finals, there is no reason for it not to be in the next World Finals, and it's nice to have an advantage of knowing the right algorithms. Okay, so so that's it for problem I. That's it for today's editorial. If you'd like, I want to share. I wanted to continue with the when FFT is done over the prime modula, not over the field of complex numbers. Like almost all of you are coding in C++, and I code in Java, so you all have the standard complex data type, and this one will be easier for you. But as for me, it was easier to code the standard FFT with just one number over the prime. And yeah. If you'd like, I want to share some how it's different from complex numbers and what you need to know to code the FFT this way. So it won't be long, I promise. Okay, so here we consider the field over the prime. So all the operations are made modulo p. And first of all, the p should be equal to some constant multiplied by 2 to the power of k plus 1. This is the important condition for the FFT to work over this modulo, because we need for this root of unity to exist, and it will exist if the modulo is of this type form. Okay, so first, how to find this kind of prime? If we say we want to have k at least 20, how would you find this kind of prime? Sorry? Yes, just go for c from 1 to infinity and check if c multiplied by 2 to the power of k plus 1 is prime. Primes are distributed somewhat randomly in this kind of arithmetic sequences, so you'll find one eventually, and it would take time proportional to, I'd say, k, because the primes are distributed as 1 over log p. So this one won't take too long. If you are implementing your FFT often, I suggest that you just remember the p. For example, I use the p equal to 7 multiplied by 17 to 23 plus 1. The best number on the earth. And it's somewhat equal to 10 to the power of 9. So it starts like 9, 9, 2, something. Okay. So the next part is to find the omega for this one. And since we know from what we know from number theory is there exists a generator G such that G0, G1, and G minus 2 are all different. So for all prime P, there is one prime G. Not prime, but some number G. Okay, so if we know G, how do we find omega? So that we don't need all of this to be different, but we only need 0 and minus 1 to be different. And we need n's power to be 1. How can we find such omega if we know G? Huh? Sorry, can't hear you.
I was wrong.
Okay.
G to the C power?
Well, not C, but almost. Yes. Well, n is not necessarily equal to the power of k, but yeah, it's almost correct. So if we set omega to G to the power of P minus 1 divided by n, this would satisfy all the properties we need. So to the power of n, this would be G to the power of P minus 1, which is always 1. And all the values before will be different. So if we know the generator for this prime, we can know omega. So the next step is how to find the generator. Turns out the generators are also distributed somewhat randomly, so we can just go from 2 to P and just check if it's a generator. And turns out it's sufficient to check if G is generator if for all divisors D of P minus 1, sorry. If for all divisors of P minus 1, that G to the power of T is not 1. So if this is true, then G is the generator. It might help you with some another number theory tasks, and yeah, so here's how you find the generator. So just iterate over all of them and check for all divisors of P minus 1. Good. Wonder, do we have time to explain the non-recursive version? Okay, so I'll try to be quick. So here we had the version of algorithm that is recursive, and as you probably know, the recursion takes time. So we can derive a non-recursive version from recursive version, and here first I wanted to do an example for how the algorithm actually splits the indices. So first we have all the indices from 0 to 7, then 0, 2, 4, 6, 1, 3, 5, 7, 1, 5, 3, 7. Yes. 0, 4, 2, 6. So in the end, the first array will be called with A0, the second the second array of length 1 will be A4, then A2, then A6. Do you know what this order is? It's not some kind of random order. And do you know what this one is? Yes, if we write them in binary and reverse the bits, this will be ordered as the bit sequences. So we have this array A, and we'd like to perform all these DFTs in place. So the first step would be perform all the DFTs of size 2. The second step will be perform all the DFTs of size 4. And so on up to n. So here I'll just have like the schema of the algorithm. I'm afraid I don't have enough time to write the algorithm. Okay, first we permute A in according to reverse bit sequence. Second, then we'll just perform DFT of size 2, 4, 8, up to n. So multiplying by 2 each time. So then we'll have the loop, the same loop as this one, to perform to merge the two DFTs in place. So first we'll loop over which kind of DFT we are performing. So this would be the first one, second one, third one, so on. Here I write our kind of C code, I guess. And we step and our step will be the length of the DFT. So here, first one, second one, third one. So then we actually make the same loop as in recursive algorithm. So j is less than len over 2. And here, the role of like a waved 0 and a waved 1 will serve there. So let's say u is a I plus j, and v is plus j plus so these two values are the same as these two values. And after that, we'll just assign them here. It will be equal to u plus v multiplied by at the level. When we do DFTs of size len, we actually use the roots of unity of size m divided by len, which is somewhat intuitive because each time we recurse, we multiply, we divide our n by 2, and this is how much we divided our n by. Here, to the power of j, and update the other value the same. So this is like the short version of the non-recursive algorithm. I understand it's hard to get from like the first loop. If you didn't know the algorithm before. So yes, this is the kind of non-recursive version of FT algorithm, and it's usually faster, but I don't actually know how fast is this one. So it's up to you to check, I guess. Okay, guess that's it for today. See you in the contest floor later.
You said you used this value of b for the
7, 17, 20.